Hey everyone, welcome to this explainer on summing amplifier circuit design. Today we're going to take those dry, abstract nodal equations and turn them into the actual real-world magic of mixing signals.
Picture this. You've got a band, say a guitar, vocals, and drums. How on earth do you plug all of their instruments into one single speaker output without it turning into a distorted, messy wall of noise? It's a pretty serious engineering challenge, right? Well, the solution is what you see here, an audio mixer. And the real star of the show, hiding right inside, is the Summing Amplifier. It's this ingenious op-amp circuit that takes multiple inputs and seamlessly blends them into one clean output. It basically acts as the ultimate analog traffic cop. Moving to our first section, the secret sauce, op-amp's golden rules. To get how this perfect isolation works, we really need to quickly look at the ground rules of op-amps. It literally all boils down to two golden rules. First up, the current rule. Basically, zero current flows into the op-amp inputs, none at all. And second, the voltage rule. The op-amp works around the clock to force the voltage difference between its positive and negative terminals to exactly zero.
Section 2, the inverting summing amplifier design. Let's see how these golden rules actually shape the most common summing circuit. Take a look right here at the node marked X. Because of that voltage rule we just talked about, the junction where all our input signals meet is held at what we call a virtual earth of 0 volts. So, the absolute key takeaway here is that this acts like a perfectly isolated traffic intersection. The signals mix together, for sure, but there's absolutely no way for them to backfeed into each other. And honestly, that beautiful isolation makes the math incredibly easy. If we just keep all our input resistors exactly equal to the feedback resistor, the output is literally just basic addition. We just add up our input voltages, V1, V2, and V3. You just have to keep in mind, it is inverted to a negative value, since we're feeding them all into the negative terminal. Now you might be wondering, what if you actually want the vocals louder than the drums? Easy. You just change the specific input resistor value for that channel. This creates what's called a weighted sum, which essentially scales that specific input. You can literally think of those resistors as your individual volume knobs. Next up, inverting versus non-inverting summing. Producing a negative sum is great, but what if your application specifically requires a positive voltage output? Well, we can absolutely use a non-inverting setup to get that positive sum, plus a higher input impedance. But yeah, there's a huge catch. We completely sacrifice that perfect virtual earth isolation we just talked about. And worse, it requires some seriously tricky math to balance the resistor weights, because the current flowing into one resistor suddenly gets affected by the voltage at all the other inputs. Not ideal, right? Finally, real-world use cases. So beyond our audio mixer example, where else do engineers actually deploy this mathematical analog magic? These little circuits are the unsung heroes of analog electronics. We use them for all sorts of things, from applying a steady DC offset to a raw, jumpy AC sensor signal, to just calculating a real-time analog average of multiple inputs, simply by matching up resistor values. But check this out. One of the most elegant applications is the digital-to-analog converter, or DAC. By using summing amplifier input resistors that literally double in value, like 1K, 2K, 4K, 8K, we can physically represent binary bits. This simple circuit perfectly translates your digital ones and zeros into a smooth, proportional analog voltage. It's brilliant. Which brings up a pretty fascinating thought to leave you with today. If just this simple little arrangement of resistors and an op-amp can reliably add, average, and scale, what kind of circuits are out there doing advanced calculus, like integration and differentiation, right under our noses in the analog realm? Definitely something to chew on next time you pick up a piece of electronics. Thanks so much for joining me for this explainer, and keep exploring.